What's happening, guys? How's it going? Today we're gonna solve this problem here. So instead of looking for just bending moment, we're gonna solve a shear, bending, and axial force diagrams. So here we have frame. We have here we have a y-x. As you may guess, this is 0, and you have EY. So here we got 5 kilonewton meter UDL, and equivalent load of this UDL gonna be placed right here, and it's gonna be 5 times 7, right? 35. So what do you think AY and EY is? Well, EY is gonna be 35, and this is gonna be 0. You can check this using sum of moment around point E. This direction is positive, and you can do, well, all you have essentially is just AY times 3.5, and it's rotating, trying to rotate clockwise, so it's negative, equals 0, so AY is equal to 0. We just proved it. So now, when you do structural analysis like this, when you need to draw shear, bending, and AFD diagrams, I recommend you do this. Separate joints from members, okay, and explode your structure like that, like how I did. You will see why it's a pretty good approach to do it. So we know that at point E, at support E, we have 35 kilonewtons, right? So let's start with the joint, since we know. So here we have 0. Here we got also 0. So now the second hint is, when you separated joints from members, you need to balance forces at members and joints. So what I mean by this, if we have at point at joint E vertical force, there must be force go in the direction to balance it, because it's statics. We don't like when sheet is moving, so that's why it has to be 0. And now the 35, so when you go now from joint to member, you have to mirror whatever you have in a joint to the member. So you mirror it, okay. Now we have to balance this member. As you may guess, there must be here 35. And now you know that this DE member is under compression because of these arrows. Right. Now is the fun part. How do I erase it? It's not going to erase it. Okay. Now the fun part. So this 35 must act also to the joint like this, because I mirror it. Remember, you mirror it every time. Now, well, we have 2 UDLs. So here we have nothing, pretty much nothing. Like there is no shear, there is no axial load. So we can, all that we need to solve now is this and that. Now, from which one to start? I would start from cantilever, because cantilever is a pretty simple case. And always start with the one that is easier to solve. So you can sort of break down 5 kilonewton meter, and what the distance there? 3.5. Okay, so this is 3.5 meters, and this is also 3.5. So equivalent load here is 17.5. Is this right? 5 times 3.5. It is. Equivalent load, you need to put this point here to show that this is equivalent load. It's not actually additional load. It's equivalent to this UDL. So it's sort of, this is sort of imaginary load, okay? Just to substitute UDL for our calculations. Now you can do, doesn't matter, you can do first shear, you can do moment first. We can try to do moment first if you like. So moment diagram, how you do it, you essentially hold it here with your hand And where is this force trying to rotate? Well, it's trying to rotate this way, right? So the beam is trying to sort of go that way. So what it means? It means simply that we, because again, that's statics, right? Nothing is moving. So we have to counter this moment, which is 17.5 times 1.75, half of 3.5 divided by 2, right? We have to counter this moment on this end of the beam opposite way. And what we have is 17.5 times 1.75 is 30.625. I'm gonna erase this. Okay, so 30.625. Moment goes this way. Does it go this way? No, not at all, because that's cantilever, and you can actually see it in the formal sheet as well. That's our formal sheet. That's our cantilever case. They actually already give us the equation actually here as well to find the max moment. You can do this equation, or you can just simply solve it the way we just did it. So what is next? Oh yeah, next is convention. So remember, some schools tell you that you have to do it like this, positive moment. Some schools tell you have to do it like this. So essentially, here they're saying you that you have to plot your moment diagram on compression side. Here they tell you that you have to plot it in tension side. For me, this makes more sense because it actually shows us the deflected shape. This one for me doesn't make sense because it doesn't show us deflected shape. So let's go with this way. I'm gonna stick with this convention. But in your case, if you have it like this and your prof told you, okay, plus moment is like that, then your diagram is just gonna be mirrored basically. So let's go with this convention here. And so how do you read this convention? Well, this arrow and this arrow tell you the side of the beam. So the end, actually, not side, the end of the beam. This is left end, this is right end. If your moment is like this, then it's positive. If its moment is like this, then it's positive on another side of the beam. So what is our case now here? Well, you see that's going to be positive moment. So I go up here like this. And because it's UDL, I have to do it like that. It's not a straight line, it's a parabolic line, okay? And this is our 30.625. Again, if your prof tell you to do this convention, your diagram will just be mirrored like this, okay? That's the whole difference. But we're gonna, for this example, we're gonna go with, go with this convention, okay? Okay, so remember, you have to now, we have 30.625, so it means that here you have also 30.625. That's the beauty of separating joints from members. You just pretty much every time you have something on a beam, you mirror it to the joint and vice versa. So it seems like we solved it for a moment here. So let's go to this side of the beam. Well, it turns out to be exactly the same. 17.5. You hold it here where it's trying to rotate. It's trying to rotate this way, that way, right? This way is a rotation of the beam. So you don't want it to be rotated because it's statics. You want your house to be statically positioned, I don't know, so it doesn't have, you don't like moving houses, so you have to counter it like this. And 30.625, that's a countered moment for this 30.625. So now we're gonna erase this. And again, our convention tells us that, hey, we're on the right side of the beam, right? So this is right side of the beam. On the right side of the beam, positive moment is down. So that's exactly what we have. So your moment diagram will be exactly same like that. Okay. Nothing goes here. There is no moment here, so it's just been. So that's our case, and we have here 30.625, and now you will see the magic. So 30.625 kilonewtons on the end of the beam. We mirrored, okay, 30.625, and now you see that they cancel out. Actually, this will cancel this, which what we want. We just proved equilibrium. So moment diagrams are done. Let's do a shear diagram. Okay, so let's start from here. 17.5 acting equivalent load, right? That's equivalent load. Acting in the middle. So I have to counter it again by 17.5. Why not here? Because this is free end, there is nothing there. It's cantilever, right? And you also can look on the formula sheet and actually see there is nothing here, right? So all resistance gonna be on the side, on the cantilever side of the beam. Okay, so we have, so I would prefer to draw it actually below. You got the point. Go like this. So then, and we have convention. Positive shear is like this, right? Again, same idea. Left side of the beam, right side of the beam. Where we are on the left side of the beam. And it's positive because this arrow is same as this arrow, right? So what we've got is we have to, let me erase a little bit here. Let me just put it here, kilonewtons. Okay, we have to go up by 17.5, and because it's UDL, it's a straight line. Okay. Plus, there is also a trick. You can put here a little guy and you walk him downhill. So downhill is easy, it's plus. But this works only when your convention is like that. Okay, this is important. If your convention is like this, then this little guy doesn't work. You will have to go sort of uphill. So always walk from left to right. Okay, always from left to right. Left to right. If it's downhill, easy, shear will be plus. If it's uphill, it's difficult, shear will be negative. So here, as you see, you're gonna go walk up and it's gonna be negative. So you will have like this. And you can prove it as well using the method we just did. So 17.5 here, 17.5 counter it here on the side of the beam. Positive shear, remember, like this. This is left side, this is right side. What you have to do? Well, it's opposite. That's why I'm going negative. I'm going negative. And this is my 17.5 kilonewtons. Okay. And I think that's it. Yeah, that's all we need to do. And you can do this guy as well. This guy is a shortcut. Okay, going uphill, it's negative. And well, now let's just finish it off. So 17.5 here, you have to again. So from end of the beam, we have to counter it by 17.5. And this 17.5 will be countered on the joint 17.5. And now this 17.5 plus this 17.5 is countered by the 35. So everything is in equilibrium. You see? So point D. Okay. So, and so we've done moment diagrams, we've done shear diagrams. There is nothing here, no axial, no shear, no moment, nothing. And on this beam, we have axial force diagram, simply like this. Compression, I don't know where you're gonna put it here, 35. That's it. This is your D, E for today, and we're gonna solve more problems. So if you like this video, please smash the like button. Thank you.